Okay, so today we're going to be looking at energy levels in atoms and line spectra. So from your syllabus, you need to know about these discrete energy levels in ionized atoms, which we'll go into. You then need to understand the appearance and formation of emission and absorption spectra, and then we're going to use an equation to explain this. So this all comes from, or it can be best explained at least by thinking about astronomy. When we look at a particular star, what we tend to see, or from nebula, is we see a spectrum of light, but we actually find bands within this light. And what we notice is that depending on the element that we're looking at, we see particular patterns within the spectra. So you can see here's the spectrum of a particular star, and as you examine it, you can see there's lots of different bands here. And what astronomers are able to do is match up the locations of the bands here with known bands from just sitting in a lab. They can look at it, and that gives them the composition of the star. And from that, they can figure out what the star is made of. And if you're a chemist, you're probably familiar with doing this as well in chemistry. You can just with any sample and see what it contains based on its spectrum. And there are two types of spectrums. What we see is that cool gases, they have absorption spectra. So in an absorption spectra, this is the light that if you shine pure white light through it, we see these missing bands here of wavelengths that aren't present. You also get emission spectrums. So an emission spectrum, that happens where if you make a gas really, really hot, and then what you see is that bands only appear at given wavelengths. Now, the fact that these exist, they give us a suggestion. And what they suggest to us is that any particular element, well, it can only absorb or emit particular wavelengths of light. Because, like I say, we see these as very, very narrow, very thin bands associated with each atom. Now, since we know that the energy of a photon is Planck's constant multiplied by its frequency, or we can rearrange it to hc over lambda, well, that tells us that gases only absorb or emit specific energy values. We know that from this equation, this red light over here, that's relatively low energy. Let's put this over here. So this is going to be low energy. Over here, these purple wavelengths, they're very high energy. So we can see that there are different energies being emitted or absorbed by gases. And what we need to do is try to explain that. And the classical explanation, or sort of the common explanation given, looks a little bit like this. So you know from really year 7 chemistry, I suppose, that atoms, we typically draw them like this. Remember the dot cross notation? So we say that atoms can have 2 electrons in the first shell and 8 electrons in every other shell. If you've done A-level chemistry, don't ruin it. It gets a little bit more complicated in real life. Now, what we can say, and this is kind of using some of the physics that we already know, we know that there's going to be, for an individual electron, there's going to be a force acting on that electron, which is equal to the electric field strength at that location multiplied by the charge of that electron. So I can say F is EQ. Now, what quantum physics suggests is that these particular energy levels, they are quantized. So they have only allowed orbits, only allowed levels. So rather than drawing it like this, in reality, what we in lessons, what we tend to do is we draw it as almost a graph. And so you can imagine that, I guess if you zoomed in really, really far, it would sort of look a bit like this. So we're looking at just one section of these shells. So we kind of, rather than it being curved, we turn it into a straight line. And we say a couple of key terms. The first one is we say that the lowest energy state of an atom is called its ground state. So if you have simple hydrogen, then that would be 1 electron in the first shell. If you have a noble gas, it would be 1 of the electrons from the outer shell. And again, if you've done chemistry, you're probably familiar with this. Now, what we can say is that when an atom's in the ground state, or when a particle is in its ground state, and it absorbs energy, well, that allows an electron to go from the ground state up to a higher energy shell. And again, chemists may be familiar with this, but what this means is that for real atoms, you actually quite rarely have all the atoms sitting in that nice, neat configuration that we taught you all the way back in year 7. Instead, you actually have electrons jumping up and down all the time. And depending on, if you make it hot, say, well, when you make it hot, you give it lots of energy, and you might make it hot enough to jump up to this energy level here. Now, if you remember earlier, we talked about electron volts. Because we're dealing with tiny little electrons, very low charges, we tend to refer to this in electron volt terms. So at the ground state, it's not excited at all, but we can say that in order to remove that electron, or to make it go up from the ground state up to there, we'd need, for instance, for this one I did about 7.3 electron volts of energy to excite it. However, in most physics terms, same as we did kind of previously, what we usually do is we say that down here is the ground state, and then when we're actually talking about the individual energies, we usually say that excitation is 0, and then we make the individual energy levels negative, because same argument that we do when we're talking about gravitational potential or electrical potential. It's much simpler for all atoms to just say, well, ionized is 0, and then you're going to do, work's going to get out of the system if you allow electron to drop to a lower energy level, so we'll make them all negative. It means that way, whether you're ionizing argon or carbon or uranium, doesn't matter, they're all going to 0, and then you can kind of understand that atoms that are bigger and have a larger nuclei and take more energy to remove an electron, well, they'll have a deeper ground state, so it takes more energy. So it stops us having to be confused when electrons move from one atom to the next. Now here's the exciting bit. It turns out that we can also do this excitation by using photons, and that kind of makes sense when we think about that spectrum that we were seeing. So what happens is, we can have an electron sitting here in its shell, and when it absorbs a particular photon, it is able to move up to an outer shell. And we kind of draw that on the diagram like this. Yeah, we draw it as going from maybe the n is 1 electron level up to the n is 5. What's also interesting is that we see that, well, once that electron's moved up, it's able to drop back down. And if it drops back down again, then we find that it emits a photon instead of absorbing one. And what's particularly cool is we can find that it can do this by different states. So what we can see is we could take an electron that's sitting here in the ground state, and we could excite it. So we could excite it with either heat energy from its surroundings, or I can say we'll excite it with a photon. Now that photon will allow it to be promoted up to a higher energy level. And what we will see is that later that electron that will be sitting in this energy level, it can now drop down through other energy levels. And the cool thing is that each of these will emit light. Now here it's dropped down quite a small change in energy, so I'd see quite a long wavelength of light because the energy here is quite small, and we know it is HF, so the frequency is going to be quite low. This gap is a little bit smaller, sorry, a little bit bigger, so it's a little bit more energy, so I might get a slightly shorter wavelength, higher frequency, and this gap is quite big. So here I'd have this as maybe a blue photon, and really actually to have made this excite, I guess let's change that then. I'd have to have this as a sort of a purpley light of a very short wavelength in order to make it jump up like that. And because these energy levels are fixed, what we see is that this only happens at these very unique frequencies. Because I know E is HF, in this instance I can say, well, the energy is the difference between these two. And whatever these two differences are, that must be the energy of the photon, and that will give me the frequency that these photons have. Now we typically write that using this equation. We say that the difference between these two energy levels is HF, which again is HC over lambda. So when you're given a spectrum, and again a typical question will give you something like this, when you're given one of these, you can just say, well, in order to go from one energy level to the next, I find the difference in energy between them, and that gives me the required frequency. If we put that all together, then this explains what we see. Right? We see from the light that if it's, and let's go with the emission, if it's emitting light, that means that electrons are dropping down to lower energy levels. Electrons can only drop down through allowed energy levels, so that means we only see specific wavelengths of light that are given off. Absorption spectrums are kind of similar. A typical example of that would be you have white light that shines through something that's cooler. Now, as it's shining through something that's cooler, what's happening is within that cold gas, the atoms inside it are absorbing the photons that correspond to the energy levels that exist within that sample. So because they're absorbing it, you get a black line that appears there. And so these two together allow us to do quite a lot of useful chemistry, quite a lot of useful astronomy, and also serves to provide a lot of evidence about the nature of quantum mechanics. So it's a pretty useful tool. Often the simple questions, you're quite lucky if you get something just around this equation. The much trickier ones are when they ask you to explain it. So make sure you're confident with that explanation of what's going on and why.